In this video, we're going to discuss the solutions to the final exam on Calculus 1 course. So the questions are intended to test the students' knowledge on the following topics. So it's about the derivatives, their meaning, their techniques and applications of the derivatives, and there are questions on the integration, the meaning of the integration, integration techniques, and applications of the integration. And also there are questions on the calculus of parametric equations, and also a couple of problems on optimization using the derivatives. So the first question, so the exam consists of two parts. The first part is the short answer questions, and the second part is the problems which is needed to write the full solutions. So problem number 1, for a given function, we need to evaluate the derivative of this function and the derivative at some point, at a given point 0. So in order to take the derivative of this, we need to take it as the derivative of the power function. So the derivative of the power function is n multiplied to the x in the power of n minus 1. So that is why derivative of this function, I'm going to take it as derivative of the x cubed. So derivative of the x cubed would be simply 3x squared, right? So that is why derivative of this function would be 3 multiplied to this function multiplied in the square. And then additionally, I need to multiply this to the derivative of this function separately. So derivative of this function without the cube is going to be tx. So I need to multiply this to the dx additionally. Now, I've found the derivative of this function. I need to evaluate this function, derivative of this function at the point 0. So basically, I need to substitute the 0 to here, to here, to here, to the 3 axes. So if I substitute the 0 for all the axes, I'm going to get 0. So derivative of this function at the point 0 is equal to the 0. Problem number 2, we need to evaluate this integral. And I see a function and its derivative inside the integrand. So I see the function x cubed plus 1 and its derivative 3x squared inside this integrand. It means that I can use the substitution rule. So my substitution would be u is equal to x cubed plus 1. And if I differentiate both parts, I'm going to get du is equal to the 3x squared dx. And now I can substitute this part, x cubed plus 1, was the u, and 3x squared dx was the du. So I will get this integrand. So after integration, I will obtain minus cosine of u, and I can resubstitute the u with the x cubed plus 1, and I will obtain the answer. Problem number 3, we need to evaluate the antiderivative of this function, which is really straightforward. So in order to find the antiderivative of the first term, I need to know how to take the antiderivative of the power functions. It is the antiderivative of the power function xn is going to be xn plus 1 over n plus 1. And antiderivative of the sine is going to be minus cosine. So the antiderivative of the x9 is going to be x10 over 10. And this 8 is going to be cancelled, and I will have just 4 over 5 x in the power of 10. And antiderivative of the minus 3 sine of x is going to be plus 3 cosine of x. So here's a mistake, so it should be plus here. So find the limit of this function. So this is so-called the indeterminate limit, because if I substitute the 0 to here and here, I'm going to get the ratio of the 0 over 0, right? Because cosine of 0 is 1. So this is going to be 1 minus 1, which is 0. And in the denominator, I will have 0 again. So in order to evaluate this kind of limits, we can take the derivative of the numerator and denominator separately and evaluate that limit. So let us find the limit of, so find the derivative of the numerator. It's going to be equal to the 0 minus sine of 4x, right? So the derivative of the cos minus cosine of 4x is going to be equal to the minus sine of 4x, right? And additionally, I need to multiply this as a 4. And derivative of the x squared is equal to the tx. So this limit is going to be equal to this limit. So if I substitute the 0 here, it's going to be again 0 over 0 limit. And I need to take the derivative again. So this limit is equal to the derivative of the numerator separately and derivative of the denominator separately. So the derivative of the numerator in this case is going to be equal to the cosine of 4x multiplied to the 4, which is equal to the 16 cosine of 4x, and derivative of the tx is equal to the t. Now if I evaluate the limit, so the cosine of 4x is going to be cosine of 0 if I substitute x to be equal to the 0, and I will have 16 over t, which is simply 8. Number 5 is about the composite functions. If we're given t functions, we need to evaluate the composition of the f and g at the point 4. So what I'm going to do is I'm evaluating the g at the point 4, then I'm evaluating the f at the g of 4. So let's evaluate what is a g of 4. So let's evaluate this inner function here. So g of 4 is, I'm just going to substitute 4 here and 4 here, right? So square root of 4 plus 1, which is going to be 3. So this is g of 4. Now what I'm going to do is, I would like to substitute the g of 4, which is 3, to the f. So this is going to be equal to the f of 3, which is equal to the 1 over 3. So problem number is 5 or 6 already, right? So we need to take the derivative of this function. So the derivative of this function is going to be equal, so we are going to use the chain rule, right, again. So derivative of the ln of x is going to be 1 over x, so the derivative of the ln of x squared plus 1 is going to be 1 over x squared plus 1, and additionally multiplied is the derivative of the x squared plus 1, which is going to be equal to the tx, right? So this is going to be equal to the 1 over x squared plus 1, and then additionally multiplied to the tx, which is the derivative of the x squared plus 1. So this is going to be, so let's discuss the problems from the section 2. So we're given the parametric curve was the equation x is equal to the sine cube and y is equal to the cosine cube. We need to find the equation of the tangent line to this curve at the point theta is equal to the pi over 6. So in order to find the tangent line to the parametric curve or to any curve, we need to perform the 3 steps. So first of all, we need to find the slope of the tangent line m by finding the derivative of the y prime at this point, at a given point. So derivative of the y with respect to the x when the curve is given parametrically is equal to the derivative of the y with respect to the theta divided to the derivative of the x with respect to the theta. So the derivative of the y with respect to the theta is going to be equal to the 3 cosine of theta multiplied to the derivative of the cosine, right, which is minus sine. And derivative of the x with respect to the theta, it's going to be 3 sine of square of theta multiplied to the derivative of the sine of x, which is cosine of x, right? So 3 cosine squared multiplied to the derivative of the cosine, and 3 sine squared multiplied to the derivative of the sine. So I need to evaluate everything here at the point pi over 6. So cosine of pi over 6 is equal to the square root of 3 over t. So in the square it's going to be 3 over 4. Sine of pi over 6 is going to be 1 over t. So if I substitute here 1 over t in the square, which is going to be 1 over 4, and here square root of 3 over t, I will get this term. So this 3 and this 3 are going to be cancelled. This 4 and this 4 are going to be cancelled. This t and this t, and the only thing which is left is this 3 and this square root of 3. If I subtract them, delete them, I will get minus square root of 3. So in step number t, we need to evaluate the coordinates of the point which is in the intersection of the curve and the tangent line together. So basically x0 and y0 at this point, theta is equal to the pi over 6, passes through the point and the curve, the tangent line at the same time. So x0 is equal to the sine cube of pi over 6, which is equal to the 1 over 8, right? Because sine of pi over 6 is 1 over t. And y0 is cosine cube of pi over 6, which is equal to the 3 square root of 3 over 8, because cosine of pi over 6 is square root of 3 over t. So and the step number 3 is we need to find the y-intercept of the line, which is found by subtracting the mx0 from the y0. So we just need to substitute all the things which we found in the first 2 steps. So y0 is going to be 3 square root of 3 over 8, m is equal to the minus square root of 3, and x0 is equal to the 1 over 8. If I substitute everything here, I will get this term, this minus and this minus is going to be plus, and I will have 4 square root of 3 over t, or square root of 3 over t. So the equation of the tangent line is written in this form, where m is the slope of the line and b is the y-intercept of this line. So problem number 2 is we're given this kind of function right? So x is not inside this function. X is on the border of the integration. We need to find the derivative of the f. So according to the fundamental theorem of calculus 1, derivative of this function is equal simply the function which is inside the integrand. If the argument of the function is on the border of the integration, then the derivative of this function is going to be simply the integrand with respect to this argument, sine of x. So you can check it by integrating this function using like as a definite integral, and then taking the derivative with respect to the x, you're going to get the same answer as the sine of x. So in the second part of this problem, we need to sketch the derivative of this function, which is simply sine of x, right? And show the intervals where the function is increasing. The function f of x is increasing, right? So this is the graph of the sine of x, and note that the function itself, f of x, is increasing when the first derivative of the function, f prime of x, is positive, right? So from here I see that the sine of x, which is the first derivative, is positive from 0 to the pi, so that is why the function f of x is increasing from 0 to the pi. Problem number 2.3, we need to evaluate this integral. So this is the rational integration. When the idea of integration of this function is to split this integral into the two parts, right? So because integrating this integrand and this integral is much easier. So the only problem is we need to find out the values for this coefficients a, b, and c, so that when I add these two fractions, rational function, it's going to give me this function. So in order to find a, b, and c, I'm going to multiply the both parts. I would like to give the common denominator here and multiply the both parts to this denominator. So if I do this, I'm going to have, in the left hand side, I'm going to have simply 10, and in the right hand side, I will just give the common denominator and multiply this to the x minus 1, multiply to the x squared plus 9. So if I do this on the right, I'm going to get this term. Now I would like to regroup them in terms of the x squared, x, and the free coefficient, right? So the coefficient before the x squared is going to be a plus b, coefficient before the x is going to be c minus b, and the free coefficient is going to be 9a minus c. So I need to equalize the polynomial in the left hand side and in the right hand side, and the two polynomials are equal if and only if their corresponding coefficients are equal. So so the coefficient before the x squared on the right should be equal to the coefficient before the x squared on the left. So the coefficient of the x squared on the left is equal to the 0, so that is why a plus b is equal to the 0. So c minus b should be equal to the coefficient of the x in the left. So the coefficient of the x in the left is equal to the 0, so that is why c minus b is also equal to the 0. And 9a minus c is equal to the free coefficient on the left, which is equal to the 10. So 9a minus c is equal to the 10. So we've got three equations and three unknowns, and by solving them, we can find the values for the a, b, and c. So we can do some algebraic simplifications and find a solution here. So the system has the following solution: a is equal to the 1, b is equal to the minus 1, c is equal to the minus 1. Now what I would like to do is I would like to substitute them to my integration. So do you remember in the beginning the idea was to write down this rational integration as the sum of the two rational integrations, right? And here I'm just going to substitute the a was the 1, b and c was the minus 1, and now we'll obtain these two integrations. So the first integration, the first term, is very straightforward, right? So this is going to be simply a ln of x minus 1 plus some constant. And the second one, which is x plus 1 over x squared plus 9, is going to be integrated in the following way. So I'm going to again separate this integration into the two parts. I'm going to divide x squared plus 9 to the x plus 1 divided to the x squared plus 9. So I would like to write this integration as this should be equal to this integration plus this integration. So indeed this rational function plus this rational function is going to give me x plus 1 over x squared plus 9 because they have the common denominator. So integration of the first part is again straightforward because we can use the substitution rule, right? Because you see, so here's the function and its derivative is here on the numerator, so which is going to be tx simply. So that is why the integration of the x divided to the x squared plus 9 is going to be 1 over t ln of x squared plus 9, and the derivative of the second term is going to be equal to 1 over 3 arctangent of the x over 3 So we are using this formula, so the standard formula, integration of the 1 over x squared plus a squared is equal to the 1 over a arctangent of x over a. So the final answer is going to be equal to the ln of x minus 1 minus 1 over t ln of x squared plus 9 and minus 1 over 3 arctangent of x over 3 plus c. So problem number 4 is about a optimization problem, right? So we need to find the area of the largest rectangle whose base is along the x-axis and whose top cornice lies on the parabola. So let's first of all draw everything in order to imagine what we need to do. So the parabola was the equation 3 minus x squared is looking like this, right? So this parabola looks downward. So we need to inscribe a rectangle inside the parabola in such a way that its base is going to lie on the x. So let's assume, so the bottom corners, bottom edges of the rectangle are at the points minus a and a, right? So if the bottom edges are in the points minus a and a, then the top edges are going to be in the points a and f of a, and this point is going to be minus a and f of minus a. So I need this f of a because I would like to evaluate the height and the width of this rectangle. So the width of this rectangle is going to be ta, right? So the distance from here to the a is a, so that is why the width is going to be ta, and the height is going to be 2f of a. So since I know that, so f of a is the equation of this parabola basically, right? If you know the point here, and the coordinate of this point is going to be a and f of a because this point is lying on this equation, on this parabola. So the area of this rectangle is going to be equal to the TA multiplied to the TF of A, or basically 4A multiplied to the F of A. So let us substitute the f of a was a 3 minus a squared. So do you remember f of x? The equation of the parabola was 3 minus x squared. So that is why f of a is going to be equal to the 3 minus a squared. So if I substitute this, I'm going to get this equation. If I open up the brackets, I'm going to get this equation, 12a minus 4a cubed. So in order to maximize this, so I needed to find the largest possible rectangle, right? So the area of the largest rectangle. So I need to maximize this function. In order to do this, we need to take the derivative of this function with respect to the a and equalize this to the 0. So if you take the derivative, it's going to be 12 minus 12a squared. So if you equalize this to 0, you're going to get the two solutions for the a. It's going to be 1 and minus 1. And the maximum area is reached at the a is equal to the 1. And this is equal to, so maximum is reached at the a is equal to the 1, but this is not a maximum area, right? So in order to evaluate the maximum area, we need to substitute the a to here or to here. It's going to be equal to the 12 minus 4, which is equal to the 8. So note that the second derivative of the a is equal to this one, and this function is negative for all the values of the a are positive, right? So when the second derivative of the function is negative, it means that the function concave downward, right? And for extremum points, for the values of the extremum points where the second derivative is negative, so the function is going to reach its maximum because it looks down, right? It is concave downward. So for all positive a, values of the a, for example, a is equal to the 1, second derivative is negative. So that is why at those regions, so function is reaching the maximum. Okay, so this is the proof, intuitive proof, how to show that the function reaches the maximum, not the minimum at this point. And the last problem is about the application of the integration when we need to find a volume. So a cup of wine glass has a shape formed by rotating the parabola around the y-axis, and we're going to find its volume, right? How much wine does it hold? So it looks like roughly like this. So we've got a parabola, the equation of the parabola y is equal to x squared, and by rotating this around the y-axis, we can get the shape, and the radius of this upper bottom is equal to upper top is equal to the 1, so that is why this is at the point 1. So now the idea of finding the volume would be to just cut this to the many slices. If I just cut this at some point y, the radius is going to be equal to the square root of y, because so if I know the y in this equation, I can find x by taking the square root of y, right? For example, if the y is equal to the 4, or 1 over 4, then x is equal to the square root of 1 over 4, right? Because if you substitute square root of 1 over 4, it's going to be 1 over 4 on the left. Okay, so here the idea is we're going to make the slices in the y direction and horizontally in the y direction. So that is why if you cut this at some point y, the coordinate of this point is going to be square root of y and y. And the radius of this slice, which is a circle, is going to be equal to the x coordinate, right? Because it is going to give you the distance from the y-axis until this point, which is equal to the square root of y. So the area of this circle is equal to the pi r squared, where the r is equal to the square root of y, so that is why it's going to be pi y. So the volume of this object is going to be equal to the integration of the area at some point y, where the y is going to change from 0 to the 1. So we just need to substitute pi y instead of a and integrate this. So its integration is equal to the pi y squared over t, and we need to evaluate the integration at the 1 and 0. If you evaluate this at the 1, it's going to be pi over t. At the 0, it's simply 0. So that is why the volume of this object, of the solid, is equal to the pi over t.